Hi, my name is Jack Saltzman, and today I will be going over the physics lab for spring oscillation. So to introduce the lab, the purpose is to analyze the motion of an oscillating spring compared to a code model. For the code model, we used GlowScript, as we always do. The principles used are to the right here. We have spring force, work energy theorem, and Newton's second law. And the system of the experiment is a spring and ball, and the source is the Earth. Preview of what is discovered: energy is conserved, and spring does oscillate similar to the code, not exactly, but we'll get to that later. So here's the quote-unquote experiment. Our group did not choose to make our own. We followed this video. And after the video, we used Tracker to determine motion data, and the spring was calibrated for the correct scale using the lecture videos. The data from Tracker was put into a spreadsheet to be used for the lab and to be uploaded into the GlowScript. And the possible sources of error could be air resistance, a faulty spring, human error, like from the guy in the video, or an uneven weight. So here are the assumptions, initial conditions. The first is no air resistance. We did not include that in our equation. But this is just basically all the code before the while loop. So we set the variables. So we have G equals 9.8, obviously. From the data, we found the spring constant, L naught, L hat, and S, the initial kinetic, spring potential, gravitational potential, and total energies. We found the ball mass, the initial position and velocity from the video, and the timing was set previously. So here's the while loop, and basically this just updates the graphs, and we have the initial energies defined, which is basically what we set in the previous step. So we have initial kinetic energy just equals kinetic energy, and so on. We have the gravity vector, which is the same as always, mass times g, negative mass times g, in the y direction. We have the spring force this time. We have net force, which is gravity plus spring force. And then we have the Newton's second law for the velocity and position update formulas. We have to update L hat and S. And then we have to update the energies using those equations. So the observations, we observed that the model, from the model, as you can see to the right here, that the spring oscillates in an elliptical path, and the work energy principle is true. As you can see, the yellow line is flat, and the energies cancel each other out, which we'll get to later. These graphs to the far right here might be inaccurate due to error, but they're still sinusoidal, or they are accurate and the movement doesn't quite match that of the video, because the movement of the model is very precise, and it could be at a different scale. But next we have what does it mean, and this is sort of what I was getting to earlier. In the model, the energy principle is satisfied because the yellow line, which is the change in total energy, is at 0. And so if there's no change in total energy, then the work energy principle is satisfied. And then for any given period, you could see the green and red, those are the two potential energies. They cancel each other out, and then the change in kinetic energy also cancels itself out. So there's no change in total energy. So then this is the second one, does it mean? Using the graphs and Desmos, I calculated the periods. The video is set to take like the average of the periods. I just did like the first, the last lowest point minus the first lowest point, and just divided by the amount of times the system reached the lowest point in its trajectory, meaning like this. So it would be 1, 2, 3, 4, 5, and then that's what you divide it by. And the time is in the numerator. And it does make sense because in the video you can see the shape of the oscillation path is slightly wider in the x direction than it is tall in the y direction. So the conclusion, in an ideal spring oscillation system, the energy principle is met as we observed, and there's no change in total energy. The actual system was not ideal, but it was in the model. When updating the motion of the spring system, you need to consider a net force of the spring force plus the force of gravity with Newton's second law. The periods are similar but slightly different. And then for the energy principle, you need to consider every type of energy in the system. All right, thank you.